So welcome to Math 355 Abstract Algebra. This is lecture 4. And so what I want to do today is I want to talk about group homomorphisms, subgroups. We're probably not going to get to Lagrange's theorem and products of groups. I'm always overly optimistic when I write things down. You always want to make sure you don't run out of material. It is much harder lecturing for a long class than a short class because it's much harder to be sitting down, listening to math than it is to be at the board speaking. And so I'm trying to adjust what I'm doing based on that. After today, you should have a sense of how things are going. We're not going to be able to prove everything today. And so I'll be asking you if you really want to start shifting to a more flipped model where for half the classes, you watch the video at home and I lecture to the other section. And in the other one, we do a lot of problems in class. The best way to learn math is to do it, to go through all the details. All right, so let's start off with one of the key concepts of group homomorphism. So let's let G and G prime be two groups. I could have called them G1 and G2. I just need some good notation for them. And so homomorphism from G to G prime is going to be some map phi that satisfies the following property. You give me two elements in G, then phi of the product is the product of the phis. Now, when you're looking at something like this, you have to be very careful about how you read things. And you have to be very careful about the notation you use. A lot of times in mathematics, we assume you understand what we mean. It's not always a good assumption, but that's what we do. And so over here, on the left-hand side, this is multiplication in G, and on the right side, this is multiplication in G prime. So it's not necessarily the same product rule in both. It's the product rule for the group. And the understanding is it's pretty clear what's going on. If I'm combining elements, I have to use their law. This way I don't have to introduce the cumbersome notation of a dot, a multiplication dot with a subscript G and a subscript G prime. And so it's hopefully clear from context that the multiplication is always with respect to the group law from that. Okay, so anything that has this property is called a group homomorphism. And then, of course, the natural question is, why do we care? What do group homomorphisms give us? Why do we want to study them? How do we find them? Now, this has to be true for all choices of G1 and G2. Whenever you see this, you want to test it out, you want to explore, you want to see how good is this? What can this give me? Can somebody give me a good choice for G1? What could we take G1 to be? There are two natural choices for G1. So when you think of the group G, can you give me a good element from G? The identity. So let's try G1 equals E. Then we would get phi of E dot G2, and we're going to be extremely pedantic, is going to be phi of E times phi of G2. Now, what is phi of E dot G2? If I take any element and I multiply by the identity, what do I get? That element. So this is the same as phi of G2 equals phi of E, phi of G2. What would you like to deduce from this? Phi of E should be the identity. So as G2 a group, we have phi of G2 quantity inverse. Because phi of G2 is something in the group, so it has to have an inverse. So I multiply on the right, and that gives me phi of G2, phi of G2 inverse is phi of E, phi of G2, phi of G2 inverse. I'm just being extremely careful in going through all the steps. Within a week, we're probably not going to be this careful. We'll just say, and of course, from this, we can then deduce that phi of E is the identity. This is how you would put in all the steps. So phi of G2 quantity inverse is the identity E2. This is the identity E2. So we get we get E2 equals phi of E, oh, and that should be E1. Should all be E1s times E2. And then there's one last step. What is phi of E1 dotted with E2? So what is phi of E1 dotted with E2? It's just E2? Nope. Phi of E1 dotted with E2. Okay. Yeah, I mean, it is E2 from the left-hand side, yes. But if you look at the right-hand side, phi of E1 dotted with E2, what does that equal? It's just phi of E1. So therefore, we get phi of E1 equals E2. So a group homomorphism has to send the identity element to the identity element. So that is a good property to have. Okay, and this was a natural thing to try as you were looking at what's a good choice of G1. A good choice of G1 is the identity element. Let's see what it does to that. Okay, any questions about how we do this? And again, this is showing every single step. There is another choice of G1 that's a good choice to look at, and it's going to be a choice that depends on G2. What would be another good choice of G1? So before we chose G1 to be E1, yeah, take the inverse of G2. So for the next thing, let's take G1 to equal G2 inverse. So G1 dotted with G2 is G2 inverse dotted with G2, which is just the identity. So if we look at phi of G2 inverse G2, that's phi of G2 inverse dotted with or multiplied by phi of G2. And again, just showing every single step. The left-hand side is just going to be phi of E1. The right-hand side is phi of G2 inverse times phi of G2. So we get E2 is phi of G2 inverse phi of G2, multiply on the left by the inverse of phi of G2 inverse. So this is where you have to be careful how you say things. What do I want to do on the left? Let's multiply on the right. We'll multiply on the right. Let's do it this way. We'll multiply on the right by phi of G2 inverse. And then that gives us E2 times phi of G2 inverse is phi of G2 inverse, phi of G2, phi of G2 inverse. I'm getting bored. And if I'm getting bored, now again, I did this, of course, earlier today, so I have a justification for being bored. I think you're getting bored as well in terms of just how many steps we're doing. We don't want to write again on the right-hand side that phi of G2 times phi of G2 inverse is E2, and then when we multiply that by phi of G2 inverse, that's phi of G2 inverse. Let's just do it all in one step at this point. So this is just going to be E2, and so we get that phi of G2 inverse equals phi, did I move things on the wrong way? No, phi of G2 inverse. So the question is, where is the inverse? On the left-hand side, it's quantity phi of G2 inverse. And on the right-hand side, it's phi of the inverse of G2. So you want to just be careful how you say it so that it's clear what's going on. You can say things like the quantity, something like that, to just let you know where things start and stop. So the left-hand side is apply phi to G2 and then take the inverse of that. On the right-hand side, take the inverse of G2 and then take phi. So what we've seen is that when we apply phi to the inverse of an element, it's the same as the inverse of phi applied to the element. So there's really nice relationships between all of the stuff. Okay. So let's just do at least one example. And let's let Z be the group of integers under addition. So -1, 0, 1, and so on. And then in notation that we'll explain later, we'll look at the clock group. And I'm going to write it, Z is pronounced mod NZ. And this is just 0, 1, 2, ... n minus 1 under clock arithmetic. Okay. So we'll see later on Tuesday why we use this notation for the clock group. For now, let's just denote the clock group by this crazy thing. So can you give me what might be a group homomorphism from Z to the clock group? Any thoughts? So I want some map from Z to the clock group. How should we define phi of an integer m? Yeah, let's try it as this is equal to m mod n. So remainder when we divide by n. So now we just have to do the algebra. And again, if we go to a flipped class, then we'll have more time to actually go through and do all these steps. What you need to do is you need to show if mk is qk nk plus rk, then m1 plus m2 is going to be q1 plus q2 n plus r1 plus r2. This is not necessarily writing it as a multiple of n plus a remainder at most n, because unfortunately it's possible that r1 plus r2 exceeds n and we have to subtract a little bit. And so what you have to do is you have to show m1 plus m2 mod n, this is fun, is equal to m1 mod n plus m2 mod n. And then you have to take that whole thing mod n. Because the first m1 mod n is just phi of m1. It's just look at the remainder when you divide by n. The second is look at the remainder of m2 when you divide by n. And now we sum them, but we're summing them on the clock. And when we sum them on the clock, we have to do the remainder mod n. So you just have to go through and show that this works and that this is a group homomorphism. Okay? Any questions on this example? So this is a nice example. We have a non-trivial group isomorphism between the integers and the clock group. Okay. So now, proposition 2.25, we've actually already proven this. And again, you have to decide how much do you want to put in your notes? How much do you want to just say, well, look, I'm posting all the slides later. The more you write down, the more you're spending time writing and not necessarily processing the mathematics. This is one of the hardest things that you have to get used to when you go into higher mathematics. It's not at the point where you can necessarily write everything down. And it's what can I get out of the lecture? Are you taking notes in an effective way? And if not, I'm happy to chat with you about what's going on. For me, it was a real change from being able to write down everything and still have plenty of time to follow what was going on to if I write everything down, I'm spending too much time writing and not enough time thinking. So here we've already proven this. We've already proven that the identity element is set to the identity element. And we've already proven that the inverse of phi of g is the same as just phi applied to g inverse. Okay, so that's great. So we can ask about what other properties might we have. And so here's an interesting one. What do you think phi of g squared would be? How should you view g squared? G times g. So this would be phi of g, phi of g. And so phi of g times phi of g is just phi of g squared. But again, that's a little bit confusing. So I will say it's quantity phi of g squared. And my arms instinctively are doing like parentheses like this, which will not show up in the video. What do you think, building on our success of phi of g squared, what should we look at next? Phi to other powers. So if I give you phi of g cubed, how should you view g cubed? Okay, good. So first we're going to view g cubed as g squared times g, right? Exactly. So we'll have g squared times g, then that's going to be phi of g squared times phi of g. That's going to be phi of g quantity squared, phi of g. This is so exciting, phi of g cubed, right? And eventually you just start to jump to the answer. Okay, what will be true about phi of g to the n? Yeah, move the n outside, right? And how do we prove this? And for what n is this true? So we've got right now for n a positive integer. There are a couple of people I love to quote. One of my favorites is Mark Twain. He has a great quote: "A cat that jumps on a lit stove will not jump on a lit stove again, nor will it jump on a cold one. To each experience in life, only draw from it that which you should." Something along those lines. We have to be very careful. We have not proven that this holds for all n. We've only shown it holds if n is a positive integer. Hopefully this holds for other n. If n equals 0, is this true? Does phi of g to the 0 equal phi of g to the 0? Yes. Because just raising something to the 0th power is just the identity. Okay. What about negative n? Well, phi of g inverse times g inverse is just phi of g inverse, which is just quantity phi of g inverse times quantity phi of g inverse, which is quantity phi of g to the -2. And then you can argue similarly. So it is true for all n. So we know that if we take phi of g to the n, we do get quantity phi of g to the n. This is a nice property for group homomorphism. Okay, any questions about proposition 2.25? Okay, 2.25 seems good, excellent. So now, let's consider again, the integers and the clock group, z mod nz, which is 0, 1, ... and -1. We've seen that there is a group homomorphism from the integers to the clock group. But what about the other direction? Is there going to be a group homomorphism from the clock group to the integers? Do you think you can go in the other direction? And again, I've just done the section 1 lecture, so I know to some extent what the answer might be. What are your thoughts? Do you think we can go in the other direction? Okay, so can you give me a group homomorphism? So the answer could be yes, but it may be hard to construct. And there are things like that in mathematics. If you can construct something, then I'm convinced. So whenever you're not sure, let's try to build some intuition. So let's consider, as an example, let's take n equals 12, and let's take g equals 5. So g squared will mean g plus g, g cubed will mean g plus g plus g, and so on. And all of these are all a mod 12. So we all look at the remainder when we divide by 12. So let's start looking at powers of 5 or sums of 5. So let's look at powers, I'll put this in quote, of 5. So it's going to start off with 5. 5 plus 5 on a clock with 12 hours is 10. 10 plus 5 on the clock is 3. 8. What comes next? Nope. What? 1, right? 8 plus 5 is 13, right? And on the clock, 13 is 1. 6, 11. 11 plus 5 is 14, which is 2. 7, right? Did I make a mistake?
11 plus 5.
Oh, no, 11 plus 5, oops, is 14. Now I made a mistake. But I can change the 2 to a 4 very easily by going like that. Then we go from 4 to 9. 9 plus 5 is 14, which is 2. That's where the 2 is. Then that goes to 7. Then 7 plus 5 on the clock is 0. And then what comes next? 5. And so it's then going to cycle back. So if we look at what happens, if I take the element 5, it cycles back. In fact, you can show that no matter what element you take, it's going to cycle back. And the reason is we showed in last class, I believe, that if I take any element of a finite group, because there's only finitely many elements, eventually if I just keep combining it with itself, I have to get the identity. This was the pigeonhole or the Dirichlet box principle. You know, if there's only 15 elements in the group, if I consider 16 combinations of itself with itself, 2 of them have to be the same. So now if you think about what's going on in the clock group, phi of 5, you know, phi of 5 plus 5, dot, 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 and eventually phi of 5 plus 5, 12 times, that's going to be the same as phi of 0. And what does phi of 0 have to be? 0. So if I have a group homomorphism from the clock group to Z, so I want phi from the clock group to the integers. Whatever it sends 5 to, after at most 12 iterations, I've got to go to the 0 element. If phi of 5 goes to 17, then phi of 10 would go to 17 plus 17. And phi of 15 would go to 17 plus 17 plus 17. Is there any way that that can ever be the 0 element if it gets sent to 17? No. What's the only possibility for phi of 5? 0. What would be similarly the only possibility for phi of 7? 0. So the only one that works, only group homomorphism, is, you know, phi of m equals 0. So we send everything to the identity element. Let's check and make sure that this really is a group homomorphism. Is the product of 2 elements, is phi of the product of the phis? Yes, because everything is sent to the identity element, then clearly phi of the product is the product of the phis. Should we be excited about finding this group homomorphism? That might be outside my jurisdiction as your professor. You may take your excitement where you can find it. Personally, for myself, this does not really excite me as an accomplishment, right? And so mathematicians use words like trivial to describe something like this, right? And you know, it's just, of course you're going to have something like this. Don't get too excited. Every 2 groups will have a trivial group homomorphism. So the question is, when can you find something that's not trivial? When can you find something where everything is not sent to the identity? We've just shown in this situation that can't be done. because phi of 5 has to go to something. The only thing you can go to is 0. You can do this for any element because the clock group, all the elements have finite order. So that means eventually they have to iterate to the identity element. So if phi of 5 ever went to something other than 0, you would have a problem. So there is no non-trivial group homomorphism between the clock group and the integers, but there is between the integers and the clock group. So these are very different groups. So this leads to the next concept, the concept of when are two groups isomorphic? So we say two groups are isomorphic, and we'll use G1, G2. We could have done G and G prime. If there is a bijection that's a group homomorphism between the two. So I keep saying group homomorphism. The book says homomorphism. Group is understood in all of this. I like to say group homomorphism to drive home the point that I'm talking about a mapping between groups. So remember, what does it mean to be a bijection? Well, we talked about this notation, I think, in the first day of class. It means the function is one-to-one or injective. So different inputs go to different outputs. And it means that it's onto or surjective, that everything in the outcome space is hit. So the key idea or the observation is that isomorphic groups are essentially the same groups. They just have different names for the elements. And sometimes, depending on what you're doing, it's easier to see one group presented one way versus another. It doesn't really make a huge deal, but it's just good to know. Okay, now, if you have spider sense or mathematical sense, this should be a very natural question you should be asking yourself right now. I have a bijective group homomorphism from G1 to G2, if G1 and G2 are isomorphic. What else do you think I should have? So I have a bijective group homomorphism sending G1 to G2. Yeah, there should be something going the other way, right? And maybe we can figure out what that something should be. What's the only thing that can play a role in figuring out what that inverse map is? Yeah, the original map. So this is where we're going to use that it's a bijection. So a lot of what we're going to do is whenever you have a bijection, we're going to be doing it in the special case of a group homomorphism, but it's true in a lot greater generality. So over here, I'm going to have my group G1, and I'll have two elements, X1 and Y1. And then over here, I'll have my group G2, and I'll have elements X2 and Y2. And so I have a group homomorphism. So I have a map phi that takes me from X1 to X2 and Y1 to Y2. And so now I should have a way to go backwards. And so what should I send Y to? Where should Y2 be sent to under my inverse map? Y1, and similarly X2 should be sent to X1. So I want to use this to define an inverse map C. And so I'm going to have C is going to be mapped from G2 to G1 by C of Y2 is the unique X2 such that phi of X2 is Y2. Can do as there exists a unique, and this is red, there exists a unique Y, X1 such that phi of X1 equals, I'm sorry, I'm doing twos. There exists a unique X2. No, wait a minute. It shouldn't be phi of X2, I'm sorry. It should be what letter should I be using? I should be using Y1. So it should be, we define C from G2 to G1 by C of Y2 is the unique Y1 such that phi of Y1 is Y2. And we can do this as there exists a unique Y1 in G1 with phi of Y1 equals Y2. So this is where we're using the fact that we have a bijection. So why does some element exist? Well, because the map phi is onto, you give me something in G2. It has to be hit by something in G1. And why is it unique? Well, because the map is injective. So we have a way of defining this function C. So C is now defined. Okay. Have we proven that C is a group homomorphism? What do you think? So is C a group homomorphism, yes or no? It should be. I agree with you completely that it should be. Have we proven it? No, what do we need to show? So what do we have to do to show that C is a group homomorphism? We have to show that C of x2, y2 is C of x2, C of y2, right? Do you have any thoughts about what element might go to x2, y2? We have to figure out, if I give you some element here, I guess I should keep using yellow. Any thoughts about what element is sent to x2, y2? Good. So you are using one of my favorite proof techniques. It's the method of divine inspiration, right? Let me just try x1, y1 as the element that goes to x2, y2. If it works, wonderful. What's the problem with trying to prove things by divine inspiration? It doesn't always work. You're not always divinely inspired. Typically, during timed exams that are worth a huge part of your grade, divine inspiration often fails in situations like that. So what you want to do is, as much as possible, you want to have some kind of set procedures that suggest what you should be looking at, that will guide you to what I should study. Well, I need to figure out what goes to x2, y2. What do I have in play? I've got x1 and y1. Maybe it would be natural to look at what happens to x1, y1. So we know, whoops, I'm green. We know that phi of x1, y1 is phi of x1, phi of y1, because phi is a group homomorphism. And then that's the same as x2, y2. So yes, C of x2, y2 is x1, y1, and that's going to be C of x1, C of y. I'm sorry, C of x2. That better. C of x2, C of y2. And that will prove that it is a group homomorphism. So we showed that x1, x2 is what is mapped to, x1, y1 is mapped to x2, y2. So your intuition that x1, y1 is mapped to x2, y2 is correct. So we know that C of x2, y2 is x1, y1. But x1 is just C of x2. It's what got sent to x2 under phi. And similarly, y1 is C of y2. So we do know that, yes, C of x2, y2 is C of x2, C of y2. it is a group homomorphism. Okay, so this would be a proof that it is that there is a map from G2 to G1 that is a group homomorphism. That is in fact an isomorphism. If this were not the case, this would be a terrible language. You don't want to say G1 is isomorphic to G2 if G2 is not also isomorphic to G1. If they're equivalent, then it should go the same in both directions. Sometimes we do have bad notation. Who here remembers the trig function that is 1 over sine? 1 over is cosecant. And what function is 1 over cosine? Wouldn't you rather put cosine and cosecant together and sine and secant together? It turns out that there's a reason. There is such a thing as a co-angle, and that's why they're linked the way they are. So there is reason for the notation. But you always want to stop and think, why are we using the notation that we're using? And so if we're saying it's isomorphic, it should go both directions, which means we should have a mapping in the other direction, which we do. Okay. And now we have the beautiful remark 232 that isomorphic groups have identical structural properties. So for example, if two groups G1 and G2 are isomorphic, then we have the following 4 things must be true. The first statement is that if one of them is finite, then they're both finite and they both have the same number of elements. Okay, that's already enough to show that the integers and clock groups can't be isomorphic because they have different number of elements. One is finite, one is infinite. The next property is if one of them is abelian, then both have abelian. Excellent. The next one is if one of them has an element of order n, then the other one has an element of order n. And then finally, if one of them has k different elements of order n, then the other one also has k different elements of order n. And so one of the exercises in the book asks you to prove these. We'll prove the third one. That was the one that we did in the first section. Again, if we switch to a more flipped model where half the time you listen to lectures and half the time we do problems in class, we would then actually prove all of these and just do more examples. And so I will be emailing all of you about this. I think it's a more effective use of time, but I want to make sure that this is something that you want to do. So let's go through and let's very carefully prove the third one, that if G has an element of order n, then G2 also has an element of order n. And when we're doing something like this, the way proofs frequently begin is you start off by saying, what does the given imply? So let's prove 3. So proof of 3. So if G in G, let's call it, I guess, G1, is in G1, has order n, then G1 to the n is E1, and G1 to the k does not equal E1 for a positive integer k less than n. So it's very important to make sure we have exactly the right definition or consequence of what does it mean to have an element of order n. It's not that if I take the element and I raise it to the nth power, I get the identity. It's no smaller power works. Can somebody give me an element whose 17th power would be the identity in the group I'm thinking of? The identity, right? It's the only thing possible, right? I haven't told you what group it is. I haven't told you what the group law is. It's got to be the identity element. So the identity element to any power is going to be the identity. So when I say the element has order n, nothing smaller than n works. So what we want to do is we want to show that there is an element in G2 that has order n. Does anybody have any thoughts about what that element will be? So we need to find an element in G2 of order n. We know that G1 has order n in G1. Good, except we're not using the letter F because we're doing group theory. So we wouldn't use F. That's for like the calculus or the analysis people. What are we using? We're using phi. Right. You could use F, but we're using phi to represent a group homomorphism. So let's consider G2 equals phi of G1. So again, this is a natural thing to look at. Then G2 to the n is phi of G1 to the n, which is phi of G1 to the n. But what is G1 to the n? It's just E1 to the n. It's just E1. And what's phi of E1? E2. So we've proven earlier that the identity is mapped to the identity under group homomorphism. So we've shown that G2 to the n is E2. Are we done? Have we proven that we have found an element of G2 of order n? What do you think? Is this a good proof? I do not believe we have shown that n is the smallest. So is this a good proof? It's incomplete. We have to show that no smaller n works. Claim no smaller exponent works. Assume not, so L less than n works. Thus, let's say G2 to the L is the identity, then that means E2 is G2 to the L. That's phi of G1 to the L, which is phi of G1 to the L. And again, when you just say it like that, it's confusing. So I should really say it's quantity phi of G1 raised to the L. And then we use our property that if we take something to the Lth power and apply phi, that's the same as applying phi and then taking that to the Lth power, that we can bring the L inside. So now we know G1 to the L is sent to the identity. So G1 to the L is sent to the identity. Why is that a problem? So why is that a problem? So it makes G1 want to be, let me just write this a little better. So what's the problem with G1 gets sent to the identity? Why is this a problem? So L is smaller. So this is telling us that G1 has order L.
No bigger than that.
Well, do we know that G1 to the L is E1? So if we knew that G1 to the L was E1, then we would be done as you said. Only E1 because the group homomorphism is injective. So as phi is injective and phi of E1 is E2, we now know that G1 to the L has to be E1. Because you can't send two different things to the identity. So now we know that G1 to the L is E1. So violates n being the smallest power. So G2 does have order n. So it turns out we can make this a rigorous complete proof. But it was not enough to just show that if we take G2 to be phi of G1, that when we raise that to the nth power, we get the identity element. That's enough to show that it's a candidate, but it's not enough to prove that it has order n. Okay, any questions on this proof? So it's a nice exercise, try to prove some of these other statements. Okay. So now How do we prove that groups are not isomorphic? So can you give me any thoughts about how you might prove two groups are not isomorphic? Good. So if different sizes or different orders. Good, that's one way. What's another way? So one way is if they have different orders, they can't be the same. What else?
Elements can sum to like if B of n is 0, everything is.
Well, you've got to be careful. What you might be doing is you might be showing that that specific mapping is not going to be an isomorphism.
What I mean is that something.
Right, but that's just showing that a specific mapping between two groups is not a group isomorphism. It's possible, for instance, can somebody give me a group that's isomorphic to G? G. And what map can you use? Set everything to itself. So if I take the group homomorphism to be the identity map, then I get G is isomorphic to G. But if I take the group homomorphism to be send everything to the identity, then I'm not getting a bijection. So what you can do is you can show that a specific map is not a bijection, but that's not the same as showing that the two groups are not isomorphic. It just means that you can't show that they're isomorphic using that. You have to use something else. So one way to show two groups are not isomorphic is to show that they have different orders. How else could we show that they're not isomorphic?
Everything on the previous slide.
Good, good. Look at previous slide on properties. You know, if one has an element of order n and other doesn't, cannot be isomorphic. Right? So this is wonderful. So all the properties we showed, as soon as we can show that one of these properties doesn't hold in one of the groups, then we know it can't be isomorphic to the other. So the question then just becomes, when are you able to show these properties hold? When are you able to show that a group is commutative? When are you able to show that a group has an element of order n? Sometimes it can be very difficult to prove some of these properties depending on how things are presented. At some point, I will bring some of my favorite Rubik's Cubes to class. And there are some Rubik's Cubes that initially look extremely difficult and challenging. And if I say the right thing and you look at it the right way, it's like, oh, that's it. And then you can solve it by using standard techniques. But unless you look at it just the right way, it can become very difficult. And so it's wonderful to have all these properties, but the question is, when can you actually prove which of these properties hold? Okay. So now we move into section 5. And so the book has a really nice 3-step program of just really good general advice about how to analyze mathematical objects. So step 1 is deconstruction, is take whatever it is that you're studying and break it into smaller, simpler pieces. Step 2 is analyze the smaller, simpler pieces. If you can't analyze them, then it does you no good to break it into them. And then step 3 is somehow put the pieces back together. I would much rather do a lot of very easy problems than one hard problem. So for example, let's say we want to find roots of a polynomial. If I give you a polynomial degree 1, 3x plus 5 equals 0, can you find the roots of this? Yeah, right? This is not that bad. What if I gave you a quadratic? Can you find the roots of a quadratic? Yes, if not, we have issues, right? How would you find roots of a quadratic? What would you do? I'm sorry? Good. So you would either factor it or use the quadratic formula. You would factor it if you feel up for divine inspiration. If I could just look at this and sniff out how to multiply it, that's typically faster than using the quadratic formula. But if you can't look at it and see how to factor it, then you use the quadratic formula. Is the quadratic formula a big deal? No. What if I give you a cubic? There is a closed form for the roots of a cubic in terms of the coefficients. If you memorize that, you have issues. But there is a formula. It's the 21st century. We can look it up. What about the quartic? There is a closed form expression for the quartic, and it's even worse than the cubic. Now, there are some simplifications you can do to try to make it a little bit easier to memorize. It's bad. You look it up. In one of the sequels to group theory, Galois theory, you actually prove that once you get to a generic polynomial of degree 5, you can no longer write down in closed form the roots of a polynomial in terms of the coefficients. They exist. The fundamental theorem of algebra says if I have a polynomial of degree 5, there are 5 roots, but I can no longer write it down. But sometimes there's still methods you can use. I would much rather break my polynomial into factors of degree at most 4 and then just use these techniques. Ideally, to factors of degree at most 2, and then just use the quadratic formula. And then I understand each one of these, and then I somehow build it back up. So that's one of the big ideas of this course, is to try to take complicated objects, break them down into simpler pieces and understand them. Conversely, the other way of looking at this is start with simple pieces and then combine them. And then say, if I start with these simple items, what can I form by putting them all together? And so what we're going to do now is we're going to get into what's called a subgroup. And this is essentially the most obvious thing you can do. And you've seen some analogs of this before in linear algebra. So it's always nice when a prerequisite class is actually prerequisite, when we're requiring you to take it for a legitimate reason. So let's let G be a group, and then we'll say H is a subgroup. If H is a subset of G, we use the group law of G, and we want H to satisfy 3 properties. The first is closure. That if I give you 2 elements in H, their product is in H. The second one is the identity element is in H. And then the last one is that for every H in H, the inverse is in H. Now, if you remember, there were 4 properties of a group. One of those properties is not being listed here. Which one is not being listed? Associativity. Why am I not listing associativity? It's inherited. So inherited is one of my favorite words in abstract algebra. We know everything lives inside G. G is associative. Therefore, H is associative. The group operation is associative on H. Now, we don't know the other things. We don't know, for instance, that if I give you a set H, that the identity element is in H. Given that a group has to have an identity element, I need the identity element to be in H. Essentially, what we're really saying here is a subgroup is a group living in G. And so if it's living in G, it's got to have the same identity element. We know that if I take the product of 2 things in G, it's in G. But that doesn't mean that they have to be in H. That's why we have to have that explicitly as a condition. We know every element in G has an inverse, so we know H inverse exists, but the inverse doesn't have to exist in H. So that's why we have to have that as a condition. So these are extremely natural things to study. We're basically looking at a subset of elements of a group, and we're trying to see when is that a group in its own right. Now, does anybody know what is the linear algebra equivalent of this? What have you seen in linear algebra that is similar to this? Subspace. Excellent. It's a subspace. I'm really not that excited, but I drew the U too large, so I had to go to all caps. So if I let V1 through Vm be vectors in V, I can study the linear combinations A1 V1 plus dot 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 AN VM, AM VM. And this is also written as the span of V1 to Vm. So this is a subspace. So is the zero element in this set? Can you get the zero element? Yeah, just take all the A's to be zero. If you have a linear combination and you have another linear combination, you add them, it's still a linear combination. So think of this as very similar to what we did with subspaces. Okay, so now the question is, if I give you a group, does every group have a subgroup? And if so, how many subgroups does it have? So can you give me any possible subgroups? Good, you got them both. The set containing the identity element and G. What do you think we call these? Yep. And again, these are not worth being excited about. So how many subgroups does every group have? Minimum. You sure? So you're saying that every group has at least 2 subgroups minimum. Good, right? You have to be very careful. If I give you G as just the identity element, then it only has 1 subgroup itself. Okay, so be very, very careful. Think of this, cat on stove. Be very careful. We don't know that these are distinct. Most of the time they are. I mean, I guess this would be the trivial subgroup if its only thing is itself. So then the question is, do we have non-trivial subgroups? So what we can do is, consider some H in G that is not E. Do we know that there is some element H that's not E? Most of the time. And so my freshman year, I was one of the few people to enjoy the class. We had a year-long combined linear algebra, multivariable calculus, point set topology, and vector analysis. And I remember at one point the book says, when we're doing some vector spaces, that the empty vector space can cause some trouble, so we'll tacitly exclude it whenever, but we're not going to be explicit about when you should exclude it. And we'll just trust you to realize that some of these theorems might have to be slightly rephrased if you happen to be considering either the empty vector space, is that a vector space because there's no zero element, but you could phrase things such as, whenever I take an element of the space, well, there's no elements in the space, so I don't have to worry about the conclusion. You're pulling your hair at this point. Or you could consider the vector space that's just the zero element. Yeah, everything is going to trivially be true there, but it's not a very exciting space to look at. So over here, we might want to look at some G that is not just the identity element. But you have to be careful. We may not know that there is a element that is not equal to E. So we're not sure that that could happen. Consider some H and look at its powers. So we would have E, H squared, H cubed, dot, 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 and then H inverse, H to the -2, H to the -3, dot, dot, dot. So we can look at something like this. And we'll talk more about this later, but this is a very natural thing to consider. Take some element and just keep combining that element with itself. Keep adding, keep multiplying, and see what you get. That's a little bit of notation. So I apologize that this is a little bit different than what we've been using in places. For some integer D, we can form a subgroup of Z using the multiples of D. So this is going to be all multiples of a fixed D. So for example, this would be equal to minus 2D minus D, 0D, 2D, and so on. And so you can see that this is clearly going to be a subgroup of the integers. If I take two things that are multiples of n, two things that are multiples of D and I add them, I'm going to get a multiple of D. If I look at the additive inverse of 5D is minus 5D, the additive inverse of negative 2D is 2D. So the inverses are going to live in here. The zero element is going to live in here. This is going to be a subgroup. So you can show that this is a subgroup. So now, let's consider n equals 12, and let's take g to equal 5 again. So let's look at multiple powers again of 5. So we have 5. 5 plus 5 is 10. 15 is the same as 3. 8, 1, 6, 11. We then get up to 16, which becomes 4. Doing a little bit better this time. 9, 2, 7. And then what comes next? 0. So what do you notice about this subgroup? It's the whole group. So we denote, and we'll see this in the next slide, but I'll just go here. The cyclic subgroup of G is denoted by angular brackets G. You might have seen notation like this in vector spaces. So this is going to be the group generated by 5, and this is just going to be what we're calling Z mod 12Z, the clock group with 12 hours. Let's now look at the powers of 3. So it would be 3, 6, 9, and what comes after 9? 0. So it is not all of Z mod 12Z. Okay. So this is particularly good. We now have a group, and the group is the clock group. And we formed two different subgroups. The first subgroup was looking at basically multiples of 5. We kept adding 5 to itself. And it turned out that that was actually just the whole group again. We just realized something. The clock group is cyclic. It's generated by the element 5. Everything is just a multiple of 5. Is there any number that I could have used other than 5? I could have used 7, excellent. What else could I have used? 11, I'm sorry? 1, I could have used 1. What else could I have used? 11. In fact, what do you notice about these numbers 1, 5, 7, 11? They're relatively prime to 12. So we do not consider 1 prime. So do you know why 1 is not considered prime?
I'm confused.
Yep,
Relatively
prime and prime. But this is notation. So why is 1 not considered prime? Why do we exclude 1 from the set of prime numbers? It's because we want the fundamental theme of arithmetic to hold. We want every number to have a unique factorization of primes in increasing order. And if 1 was considered prime, how would you factor 6? You could say it's 2 times 3. You could also then say it's 1 to the 2024 times 2 times 3, and you would lose unique factorization. So that's why we consider 1 not a prime. It's actually a unit which has lots of nice properties. So it turns out that this group Z mod 12Z is cyclic, and it has different generators. It's generated by either multiples of 1, 5, 7, or 11. Now we can take other numbers, such as 3, and we can look at the subgroup generated by 3. And we do get a subgroup, but it's not all of Z mod 12Z. It's not all of the clock group with 12 hours. This is great. Is it the trivial subgroup containing just the identity element? No, good. So we at least know that there is at least one group that has at least one non-trivial subgroup. Right? So that this is something that's worth studying. There's at least an example of this. Okay, so as mentioned, a cyclic subgroup of G is denoted by the angular brackets around G. And by this, we mean, it's the set containing the multiples of the powers, say G to the -2, G to the -1, the identity, G, G squared, and so on. And again, some of these elements could be the same. I'm not saying these are distinct elements, I'm just listing all powers. Now, when I say that this is a cyclic subgroup, I'm implicitly assuming something by calling it a cyclic subgroup. What am I implicitly assuming is true about it? Not that it's finite, because I'm not saying that these elements are all distinct. So for example, if I look at 1, that could give me all the integers, dot, 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 -2, -1, 0, 1, 2, dot, 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 which is just all the integers. It doesn't have to be, if I looked at 5 under clock arithmetic, then if I reorder, it's the same as the clock group. So sometimes it's finite, sometimes it's infinite. But when I say it's a cyclic subgroup, what am I implicitly assuming about it? That it's a subgroup, right? It would be a horrible name to call it a cyclic subgroup if it's not a subgroup, right? But you have to prove it. So prove G is a subgroup. So the identity is clearly going to be there. If you have 2 elements that are powers of G and you multiply them, you get a power of G. Yes, so it's closed. And that holds if the powers are positive, negative, if they're mixed, that's fine. And then the next thing is you have to show that any element here, the inverse is here. So if you have G to the 5th, you also have G to the -5. If you have G to the -2, you also have G squared. So it's not so bad to just go through and show that this is a subgroup. But you have to do that. So again, every now and then somebody makes names that seem obvious, but you still have to make sure that the name is justified. You can't just say it's a cyclic subgroup without proving that it actually is a subgroup. And so it is cyclic, it's generated by one element. And we will see later in the semester that it's really convenient if you have a group that's cyclic and generated by one element. For example, if I want to understand what does phi do if phi is a group homomorphism, I just have to figure out what phi does to one element, because I know phi of G to the n is the quantity phi of G to the nth power. So if I can figure out what it does for one element, I can understand it for every element. And so I will give you the bonus comment that didn't go to section 1. Do you remember eigenvalues and eigenvectors from linear algebra? At least make me feel good and just nod your head, right? Oh yeah, eigenvalues, eigenvectors. Oh yeah, I remember those really well. Those were wonderful. And so in many situations, if you have a real symmetric matrix, turns out it has a orthonormal basis of eigenvectors. So you can write any vector as a linear combination of the eigenvectors, which means if I want to calculate high powers of A on a general vector, I decompose the vector into the eigenbasis, and then I figure out what A does to each one of them. And it just makes the analysis simpler. And we're going to be seeing, similar consequences of that in what we're looking at here. Is we're going to have these cyclic groups, and then the cyclic groups will have a generator, so maybe we can just figure out what does phi do to the generator. Well, not every group is cyclic. Oh well. maybe I can write a group as generated by a small number of elements. And if I can figure out what happens to the generators, I can then figure out what happens overall. And that's, again, going back to the theme from the start of this section. Take something complicated, break it into simpler parts, understand what's going on in the simpler parts, and then piece it all together. All right, so this is a good place to stop. So let me just stop the recording.